Greetings, everybody. Today we're kicking off scientific notation. We don't plan to spend a lot of time on scientific notation. It's very highly linked to exponents, but it is very important, and it's something that you'll see throughout your math career and in science class as well as you go forward into high school. So, what is scientific notation and why is it important? Well, scientific notation is a number written in this format right here, a times 10 raised to the n power. The base is always 10, and as you can see right here, a always has to be between 1 and 10, greater than or equal to 1 and less than 10 for a. Scientific notation is super helpful for expressing really big numbers and really small numbers that we don't want to have to write out with all the extra zeros. So scientific notation is very practical in that sense, and it helps us save time. This notes packet that I'm going through right now is available on Schoology. The key is also available on Schoology. So per usual, I'm just going to go through some examples here, and you guys can follow along by just watching the video. You can have the key up on your Chromebook as well if you want to kind of look at the key as you go, because I'm not going to do all the examples, just some of them. So this first slide, though, will give you a good kind of baseline of what scientific notation is. If you had something like 5 times 10 to the third power, that could be rewritten as 5 times 1,000. How would you get 1,000? Well, 1,000 is the same as 10 to the third power, right? 10 to the third power is 10 times 10 times 10, which is 1,000. That's how that got there, right? And 5 times 1,000 is 5,000. If I did 5 times 10 squared, that would be like 5 times 10 times 10. 10 times 10 is 100. 5 times 100 is 500. If I did 5 times 10 to the first, that's like 5 times 10, which is 50. Notice a pattern here? 5 times 10 to the 0. 10 to the 0 is just 1. Remember that from last unit? Anything to the 0 power is just 1, so that's 5. 5 times 10 to the negative first power. Well, that's like 5 times 1 over 10, which is 5 tenths, which is 1/2. And 5 times 10 to the negative second is 5 times 1 over 10 squared. That's like 5 times 1 over 100. 5 times 1 over 100. And that is 1 over 50. Now 1 over 50 is the same as 0.05. And if I backed up to 1/2, that's the same as just 0.5. Interesting. 5 times 10 to the negative third, last one, that's 5 times 1 over 10 to the positive third power, which is 1 over 200, which is 0.005. Look at the pattern here, folks. I'm going to switch colors here. What's happening every time we go to a new row? What's happening? From 5,000 to 500, that's division by 10, right? From 500 to 50, that's division by 10. From 50 to 5, 50 divided by 5, or excuse me, 50 divided by 10 is 5, so division by 10. Every time you go to a new row, you're dividing by 10. There's a reason for that, and the reason is this. The base of all of these is 10. So as the base of 10 decreases by 1, the number gets 10 times smaller. That makes sense. Every time your base of 10 increases by 1, your number would get 10 times larger. So that is a little experiment and a little foundation work with scientific notation. Let's talk a little bit about how we can express numbers written in standard form, which is just a regular way of writing numbers, into scientific notation. Here's an example right here. Notice how you can write the number 384,000 as 3.84 times 10 to the fifth power. How in the world would I get that? Let's zoom in on this a little bit. Notice how the decimal point for 384,000 is currently after the last zero right there. Look how many spaces I have to move my decimal point in order to get my first number between 1 and 10, which is the rule for scientific notation. So you may suspect you're going to have to stop right there between the 3 and the 8 to make that number between 1 and 10. So look how many spots you have to move it. 1, 2, 3, 4, 5 spots you have to move it, which is where the 5 comes from right there. You had to move the decimal point 5 spots to the left, so it's 10 to the fifth power. Your base will always be 10, and your power is determined by how many spaces you have to move. Because we move to the left in this case, it's positive. but it could be negative if we're moving the other direction to the right. And 3.84 is the result of moving that decimal point 5 spaces. You have 3.84 after that. This number right here, if I put it in my calculator, and this number right here are exactly the same. One is written in scientific notation, one is written in standard form. Let's practice writing these numbers in scientific notation. So for letter A, my decimal point is currently right here after the last 0. How many spaces do I have to move that decimal point to get my number between 1 and 10? Well, I need it to end up right here between the 3 and the 7, right? Because 3.7 is between 1 and 10. So how many spaces do I need to move it? 1, 2, 3, 4, 5 spaces. So my answer is going to be 3.7 times 10 to the 5th power. Let's take a look at the next one. Decimal point's currently right there. I need it to end up where? Between the 5 and the 2, don't I? So how many spaces? 1, 2, 3 spots I have to move it. So notice what I'm going to write here. 5.281, I have to include all those numbers, times 10 to the 3rd power. Lastly here, I want to convert this distance of 93 million meters into scientific notation. So how would I write out 93 million? Well, 93 and then 6 zeros, that would be 93 million. Currently my decimal place is right here. I need it to end up between the 9 and the 3 in order for that first number to be between 1 and 10. So 1, 2, 3, 4, 5, 6, 7 spots I have to move it. I'm going to say 9.3 times 10 to the 7th power. Well, what if I'm going the other direction? What if I have something like part 3 example, part A, where I have 6.34 times 10 to the 5th power? That's in scientific notation. I need to convert it to standard form. So the first step is to write out 6.34 as it currently appears. And this 10 to the 5th power means that I'm going to have to move the decimal point 5 places to the right. If I'm multiplying a number by 10 to the 5th power, that number is getting significantly larger. If a number is getting larger, its decimal point is moving to the right. So 1, 2, 3, 4, 5. Put zeros in the blank spaces. And there's my new number. 634,000 is my number. Why don't you guys try the next one? You can pause the video if you'd like. You start out with 3. And it's times 10 to the 7th. So 1, 2, 3, 4, 5, 6, 7 spots to the right. Fill in with zeros in the little dips. There is where you write the zeros, not on the points, but in the dips. So 30 million is your number for that one. Here's a word problem. We want to convert this distance into standard form. So currently it's 2.4 times 10 to the 5th, so I need to move 5 spots to the right. 1, 2, 3, 4, 5. Fill in with zeros. 240,000 would be your answer for that one. To this point, we've just been looking at really big numbers, converting those into scientific notation and from scientific notation into standard form. Now, scientific notation is also super helpful for really small numbers. Look at this example right here. We have a number 0.000234. I can convert small numbers to scientific notation too. Notice how I have to move 1, 2, 3, 4 spots to the right in order to make that first number between 1 and 10. 2.34 is what goes here. And then I had to move 4 spots to the right. So when you move to the right, it's going to be a negative number, so a negative 4. How can you always tell if it's going to be positive or negative? If your number is a really small number like this power is always going to be a negative. It's really as simple as that. If this number is really big, then the power will be positive. Let's try example 1 and look at A and B here. So currently here's my decimal point. Where do I need my decimal point to be if I want the first number to be between 1 and 10 for scientific notation? Would it work if it was all the way after the 7? 574 or 547 is way too big. What about 54.7? Oh, that's still too big. What about 5.47? There it is. Okay, so let's see how many spots I need to move. 1, 2, 3, 4, 5 spots. So 5.47 times 10 to the negative 5th. If you want to pause the video and try B before you continue, feel free to do that. I'm going to go ahead and look at B now. All right, I need my decimal point to end up after the 6. No, 76 is too big. What about 7.6? There is my spot. So let's go 2 spots to the right. So that's 7.6 times 10 to the negative second power. All right, let's go the other direction. So here's an example of a number written in scientific notation, and we want to convert it to standard form. So if I have a negative power, like a -3, that means I'm making the number smaller. So I'm moving the decimal point 3 places to the left. As you can see here, here's where it starts, 1, 2, 3 spots to the left, and here's my new decimal point. So I have 0.00132. It's a small number that you found by moving the decimal point 3 places to the left. Let's take a look at some examples down here. 1.27 times 10 to the negative sixth. All right, I'm going to write 1.27 first, and I'm going to move the decimal point 6 places to the left in this case. 1, 2, 3, 4, 5, 6. There's my new decimal point. Fill in zeros in the gaps. So my new number is 0.0000127. That's my new number. I'm going to do B. If you want to pause the video and try it on your own first, feel free. So 4 times 10 to the negative eighth. Note that currently 4 is really the same as 4.0, right? You can think of it as 4.0. And the decimal point's after the 4. So if I want to the negative eighth power, I need to move this 8 places to the left. 2, 3, 4, 5, 6, 7, 8. So I'm going to fill in 7 zeros. So it's point, and then 7 zeros, and then a 4. You can put the last 0 there if you want, but you don't need to. After you hit a number, if there's just zeros after it, you don't have to include those zeros. Let's look at an example. Example 4 here, a word problem. 1.23 times 10 to the negative second power. We need to convert that into standard form. So I need to move 2 places to the left. 1, 2. So my new number is 0.0123. What about the one below it? So here is my number that I have to convert here. So I'm going to write it out, 7.0 times 10 to the negative sixth. Let's move 6 places to the left. 1, 2, 3, 4, 5, 6. I'm going to fill in zeros. 1, 2, 3, 4, 5 zeros. So my new number is 0.000007. That is the diameter of a red blood cell in standard form. All right, I'm going to pause here for a moment. If you want to practice a little bit on the first 4 pages of the notes, feel free to do a few examples. Check your answers on the key. I'm going to produce another video for operating with scientific notation next. So I'm just going to kind of split the lesson today into 2 shorter videos. So you're free to watch them both right now or take a little break and come back to the other video in a second. As always, if you need anything, please reach out. Okay, let's continue our discussion on scientific notation. The focus of this video is operating with scientific notation. And this is the part of the unit that is very much intertwined with the exponents unit that we just finished. As a review from the exponents unit that we just finished, when we multiply like bases, we multiply the coefficients, keep the base, and add the exponents or add the powers. And when we divide the bases, we divide the coefficients, keep the base, and subtract the exponents or the powers. That should be review from what we just did with exponents. Now, that's coming back here with scientific notation. When you add and subtract in scientific notation, you can only collect like terms. For example, if we think about when we studied equations and stuff like that, you can only combine like terms. So in this example here, you could only combine your x's and your y's separately. So you would get negative 5x plus 2y when you combine your like terms. And similarly in the next example. The fact of the matter is you can only combine your x's and your y's. The same applies with scientific notation. If you look at this example right here, number 1, you can only combine 10 to the fourths with 10 to the fourths. These are both 10 to the fourths. Think of it almost like an x. You know, if you had 3.7x plus 2.5x, then you could combine those, right? Same concept here. You have a 10 to the fourth and a 10 to the fourth. So what you can do is you can take these coefficients and add them because it's an addition problem. And so your answer would be 6.2 times 10 to the fourth. Now, unlike multiplication and division, the power does not change. When you add and subtract, the power does not change. Just like when you add 3x and 2x, you get 5x, not 5x squared, right? It's just x. Same concept here. The 10 to the fourth stays put. All right, what about a subtraction question like this? These are all 10 to the fifth power here. That means you can treat them as like terms, and we can combine the coefficients. 2.1 minus 5.1 plus 6.3 is 3.3 times 10 to the fifth power. All right, let's do some multiplication, and we'll do some division as well. Let's do number 3. Now, this is the review from exponents. When you multiply, these don't have to be the same, right? Because you keep the base and you add the power, so 10 to the 11th power. And then the coefficients, you would multiply them since this is a multiplication question. So 2.3 times 3.3 is 7.59 times 10 to the 11th power. Let's look at number 7. Here is a division problem. We have our exponents right here that we can deal with, and then we have our coefficients. Remember, our coefficients, will divide those because it's a division problem. 6.6 divided by 3.3 is 2, and then 10 to the 15th divided by 10 to the 8th is 10 to the 7th power. Keep the base, subtract the powers. Let's do one more, number 8. Here's a little multiplication and division together. So if I was to multiply the numerator, I would get 5.3 times 1.6 gives me 8.48 times 10 to the, 4 and 9. So I'd add those to get 13. And on the denominator, I'm just going to rewrite that for now. Now I'm going to keep going. I got my exponents to deal with there. Got my coefficients to deal with there. I'm going to divide my coefficients and get 4.24 times 10 to the 13 minus 8 is 5. So that would be my answer for number 8. All right, so we just looked at operating in scientific notation. Now we're going to talk about how we can use scientific notation to determine which numbers are bigger and smaller. And as you probably have gathered to this point, the power of the base 10 is the biggest influencer of how big or small the number is. Here's what I mean by that. When I look at these two numbers, if I'm trying to determine which one's bigger, you're not looking at this number right here per se, unless the exponents are exactly the same. In this case, they're not. What you're looking at is really more this, 10 to the 8th compared to 10 to the 5th. Because 10 to the 8th is bigger than 10 to the 5th, if I was to expand this into standard form, it would have 3 extra powers of 10, or 3 extra zeros, beyond what this one would have. So therefore, this number right here is going to be much larger because of the 8th power. Well, it says how many times bigger is it? When it says how many times, you should be thinking division. How many times bigger, right? So I would do, in this case, 9 times 10 to the 8th divided by 4.6 times 10 to the 5th. And when I do that division, it's going to tell me how many times bigger the numerator is compared to the denominator. So if I do that, I will get 1.96 when I divide the coefficients times 10 to the 8 minus 5 third power. If I wrote that in standard form, it would be 1960. So here it is in scientific notation, and here it is in standard form, 1960. Let's look at the next problem here. So if I wanted to order these numbers, these 4 numbers from least to greatest, again, I'm going to focus on the power of 10 first. So when I look at these, I notice that these two both have the same power of 10, and that's -4. So if the exponents are exactly the same, then the tiebreaker goes to the coefficient. So when I consider these two numbers here, the one with the lower coefficient is this one. So that means this one would be the smallest. So I'm going to put a 1 underneath it because it's the smallest. This would be the second smallest. Now I have to compare these two. And again, they have the same exponent of 10 to the positive fourth. 2.1 though is smaller than 6.7, so that means that the first one will be smaller. So it would be overall the third largest, and this would be the largest, so it would be number 4. Okay, I'm gonna share a pretty rad trick with you right here. Secret's out here, folks. Ready for this? You can do scientific notation on your calculator. That's right, your handy dandy TI-30 calculator that you guys have had this school year and probably for the last few school years. You can use that to help you get numbers in scientific notation. For example, the first problem right there. If you type in 45,000 times 1,800, you will get in your calculator you will get 81 million, which is a massive number. And your friend's calculator may say 8.1e plus 7. What does that mean? Well, that just means that it's the same as 8.1 times 10 to the 7th power. These mean the same thing. Right here and right here, those mean the same thing. Okay? Now, you can tell your calculator to give you an answer in scientific notation as well. Okay? Now, if you go back to that original question, 45,000 times 1,800, you get 81 million on your calculator. So from there, I want you to follow these directions right here. So when you have 81 million on your calculator, hit second in the upper left corner, hit DRG, which is directly to the right of second, and you're going to see 3 options there. You're going to see flow, SCI, which is scientific, and the last one we don't worry about. Currently it's on flow, but if you scroll over to the right and click enter when the lines are under SCI in the middle, hit enter, it will convert your answer to scientific notation. That's right, you could type any problem in your calculator and your problem can convert it to scientific notation. Wow, that's helpful. So yes, when you're operating in scientific notation, you can type in the problem as it appears using parentheses, and your calculator will tell you the answer in scientific notation if you utilize this trick right here. Second, DRG, convert to scientific if you want your answer in scientific notation. And similarly, you can convert it back to flow if you want your answer in standard form. So utilize that trick. Maybe pause the video, see if you can do these last 3. I will put the answers up here as well. Okay, here are the solutions. If you were to type those problems into your calculator, you will get these answers if you are in the SCI mode, like I just talked about before. If you're not, you may get these answers. If you just type it in and you're still in flow mode, you may get this. But guess what? This means the same as this. They mean the same thing. You just have to know how to interpret it. You have to know that E is the same thing as times 10 to the whatever power, this power right here. But E means times 10 to the something power, okay? So practice typing this in your calculator, maybe even go back to some of the examples and see if you can get your answers in scientific notation in your calculator. Okay, here's the last page of the day, and you may just end up pausing your video right here so you can do these 9 questions that I've labeled out for you. So I just want you to do maybe about half of these questions. The key for this is on the agenda, or not the agenda, but on Schoology. It's linked under the folder for today. You can go in there and check your answers for these 9 questions. Use your calculator if you like to help you out on some of these questions. And there's a little progress check for you to do as well on Schoology. So make sure you check that out. These questions right here are not required. Just practice just to see if you're getting it okay. And like I said, check the key if you want to do that, and schedule a conference if you need help. Hope everybody's doing well. See you next time.